All right, so we are going to discuss solving linear inequalities. Now, when solving the linear inequalities, you would solve them just like you solve an equation. The biggest difference comes with this, guys. Whenever you have to divide or multiply by a negative, whenever you need to multiply or divide by a negative, you must reverse, switch, flip, change, however you want to say it, the inequality symbol. Now, what inequality symbol am I talking about? I'm talking about, hold on a second, let me write them down for you, the inequality symbols. Greater than, less than, greater than or equal to, less than or equal to. These are the inequality symbols that I'm talking about. So if you should have to divide or multiply by a negative, you must reverse the inequality symbol. Now, the big question is always, why do we need to reverse it? Let's take a look at an example, guys, so you can see the logic behind why we need to reverse the inequality symbol. So let's say you have this little inequality here and you need to solve it. And so you would have to divide both sides by -4. And we're going to pretend we forgot the rule that says that we have to reverse this. So we'd end up with a solution of all values of x which are less than or equal to -3 to make this problem true. Now, if that is the case, if we were to select a value that is less than -3 and plug it in here, it would make the problem true. So let's go ahead and test this theory. We're going to go ahead and check this out, guys. So we're going to take a value such as x equals to -5, which is less than -3, plug it back into the original problem for x, and then work it out and see what happens. So here, -4 times -5 gives you 20. 20 is less than or equal to 12. That's what this is saying. But this statement, guys, is completely false. There's no way 20 can be less than or even equal to 12. That's completely false. So in other words, this value right here, when you plug it back into the original problem, it doesn't make the original problem true. So there's no way we can count this as a solution. So on the other hand, if we were to reverse the inequality symbol to reflect every single value greater than or equal to -3, and we're going to test it again. Let's pick a value that's greater than or equal to -3. My favorite value to test with, guys, whenever we have to do all this testing is 0. I love testing with 0. So you will hear me say this throughout the remainder of the semester. So I'm going to choose, I'm going to check, and this I'm going to check with x equals to 0. 0 is obviously greater than -3. I am going to go back to the original problem, plug in 0 for x, and then work it out. When I work it out, I get 0 is less than or equal to 12. Is 0 less than or equal to 12? Absolutely true. So essentially what just happened is that we selected a value, which is greater than -3. And so it makes the original problem true. So therefore, every single value greater than or equal to -3 will also make the original problem true. So without reversing that inequality symbol, guys, you got the wrong answer. However, once you reverse it, you got the right set of values that will make this problem true. So now, this is the reason why we need to reverse the inequality symbol. Next, we're going to have to graph these solution sets on the number line. By the way, I forgot to mention this. Set builder notation. This is the only time I am going to mention this. Set builder notation is another way of writing the solution to an inequality. And set builder notation is nothing more, guys, than this. You're writing the solution in set notation. So first, you start off with your set notation. Identify the variable, in this case x, such that you want all x values that are greater than or equal to -3. That's it, guys. The set of all x's such that x is greater than or equal to -3. That's set builder notation. And this is the only time I'm mentioning it. You will see it. However, I'm not going to emphasize it. All right, guys. So now we're going to talk about graphing. When it comes to graphing the inequalities, guys, a couple of things you have to keep in mind. First and foremost, if you're graphing with greater than, less than, okay, you're going to have to use the parentheses for the boundary value. Now, the parentheses shows that the boundary value is excluded. It's not included as part of the solution set. So in other words, you have an open interval, and we're going to be talking about the intervals soon too. Okay, we're going to have an open interval. We'll chat about that in a minute. Okay. However, if your inequality is going to be greater than or equal to, less than or equal to, when you graph, you're going to use closed brackets. By the way, let me just throw this in here, guys. If you guys remember from grade school, okay, the parentheses are referencing the open circles, and then the brackets are representing the shaded circles. That's what they are, guys, okay? And there's a reason why you were using the parentheses and the brackets. I'll show you guys later on why we transition over to these, okay? So guys, the brackets shows that the boundary value is included, or in other words, you have a closed interval, okay? Closed interval. That's what that means, guys. All right. So now we're going to go ahead and actually graph x is greater than or equal to -3. So when it comes to graphing, I like to keep it very simple. So here it is, my number line. I like to plot my 0 on here so I can separate the negative side from the positive side. Then I like to plot my boundary value, and my boundary value is -3. Next, I am going to look at the inequality symbol. It's greater than or equal to, so this means that I need to use a bracket over or above the -3 to show that it is included or that this is a closed bracket, guys. And next, I need to decide which values on the number line are going to be greater than or equal to -3. Are they to the right of the -3 or to the left of the -3? The other thing you can do, guys, is to plug in that 0 again and ask the question, is 0 greater than -3? Absolutely true. So because the side that contains 0 is on the right, so you would go ahead and shade the right side of the number line. So guys, this is what the graph would look like. It's that easy. That's your graph. So next part of this, guys. When we are talking about solving linear inequalities, we must write the solution sets. Okay, the solution sets can be represented in interval notation. Interval notation. Many of these problems you will encounter in my math lab will require you to express the solution set in interval notation. So if you're going to write a solution set in interval notation, guys, it is simply this. You are simply taking this information off the number line over here, right there, okay? This information on the graph and rewriting it without the number line. That's all you're doing. You're expressing the same information without the number line. So there are 2 rules that govern interval notation. Rule number 1, you want to write it in numerical order. Numerical order. And when I say numerical order, you go from left to right. Just like you're reading a book. Okay, increasing order. And then number 2, you want to use parentheses with positive infinity, negative infinity. In other words, you do not ever include positive or negative infinity. So guys, interval notation takes a while to get used to. And so it's going to take a solid 3 or 4 problems for you to get used to it. Once you get used to it, you won't have an issue. So in the meantime, what I would recommend you do is to go ahead and graph the problem, and use the graph as a guide to help you write your interval notation. So for example, if I wanted to express this solution set right here in interval notation, I would go ahead and graph it and then use the graph as a guide to help me write my interval notation. So when I write interval notation, guys, I start on the left, right here, right here. On the left, I have a bracket with the -3, and my set of values, my set of solutions continue all the way to the right up to positive infinity because they continue indefinitely. So guys, this would be an expression of the solution set in interval notation. And that's it, guys. That's your interval notation. Inverse notation, it takes getting used to, but once you get used to it, it's a very easy process. So I'm gonna go ahead and do an example right now so we can go ahead and practice everything. And then I will move on to the next part of this, which are the compound inequalities, guys. So next part of this, guys, is a problem that you might see on the assignment or perhaps on the test. It is -4 times the quantity x plus 2 is greater than 3x plus 20. So on this one right here, again, you solve it just so like you would solve an equation. So you want to start off by distributing the -4. So this gives you -4x minus 8 is greater than 3x plus 20. Next, I'm going to subtract 3x on both sides. And so this leaves me with a -7x minus 8 is greater than 20. I'm now going to add 8 to both sides. And when I do this, guys, I'm left with a -7x is greater than 28. And then the last step is to divide both sides by -7. Now, when I divide both sides by -7, I have to be careful. Why? Because I'm dividing by a negative. So that's going to require me to reverse the inequality symbol, guys. Notice I'm reversing the inequality. So here, the solution set turns out to be x is less than -4. Now, they're going to want you to express this in inverse notation. Until you feel comfortable with inverse notation, personally, I would go and graph my solution and then use the graph as a guide to help me write my solution in inverse notation. So here's my 0, my -4, and then I'm going to look at my inequality symbol, which is just less than. So I'm going to use a parentheses on the -4 and show every single value that is less than the -4. So this is what the graph would look like, guys. And so now that you have the graph, you can go ahead and write your inverse notation. When writing the inverse notation, remember you go from left to right, guys, left to right, just like you're reading a book. So over here on the left, you're starting off with a -infinity, and the set of values continue all the way up to -4, but -4 is excluded. So when you write the inverse notation, it would be -infinity, comma, -4, and then just close off that parentheses, and this would be the correct answer. Someone sent me a message earlier and said, you know what? I got this problem right, but for some reason, the computer's marking it wrong. So what is wrong with this one, guys? Look, what is wrong with it? The person put a bracket when there should have been a parentheses. So this would be incorrect. There is a difference between a parentheses and a bracket. Parentheses shows that the boundary value is excluded. It cannot make the original problem true. However, the bracket shows it is included as part of the solution, as in it's a closed interval, so that it should make the original problem true. So if you want to not include the boundary value, you have to use a parenthesis. So be careful with this, guys. All right. I want to ask if you guys have any questions, but I think you guys are just waiting until we're done with the recording so you can ask your questions. So just hang on to the, go ahead.
So just a little quick. So just always change the sign for the answer?
No. The only time you change the sign is if you divide or multiply by a negative.
Gotcha, okay.
So if you're not multiplying or dividing by a negative, and we're going to do some more examples, obviously, you do not reverse the inequality symbol. In this instance, with this problem right here, we did divide by a -7, so we reverse the inequality symbol. But good question, man. All right, guys. So here comes the next part of this, guys, and that is the compound inequalities. And so for the compound inequalities, we look at two of them. The first one is the intersection of two sets. The word we use for this, the operative word, is the word and. The symbol we utilize to represent the intersection of two sets is this. Now, some people see an upside down U. Others may look at this and say, I see the letter N. Personally, I prefer the letter N, to refer back to the word and. When we talk about the intersection of two sets, guys, we're looking at all the elements which two sets have in common. What do they have in common? In other words, the elements must be in both set A and in set B. Notice I said the word and in there. The best way to show this, guys, is through a Venn diagram. So let me go to a little Venn diagram right here. Okay. I've got set A and I've got set B. Now set A has the elements 1, 2, 3. Now set B has the elements 2, 3, 4, 5. If I were to ask you to find the intersection of set A and set B, as in what do set A and set B have in common, or what elements belong to both set A and set B, that would be these elements right here in the middle, guys. And that would be the 2, the 3, okay? So it's basically what they have in common. Now, how do we show this with an inequality? So with the inequalities, guys, let me go ahead and show you a quick example of this. If I were to give you a problem like this and I were to tell you to find the intersection of these two sets, x is greater or equal to -3, and here was the operative word, x is less than 2. So we want elements which are both, okay, greater or equal to -3 and less than 2. So these elements must meet two criteria. Number one, they must be greater than or equal to -3. And number two, they must be less than 2. Both things must occur simultaneously. If they're not, then it can't be a solution. So one of the things I like to do, guys, is to plot these values on the number line and then divide up the number line into 3 regions. Here, let me use a different color. Look at that, 3 regions, okay? So we got the region on the left, the middle region, region 2, and then the region to the right, region 3. So we're looking for which one of these 3 regions has all the values that would satisfy both inequalities. And as always, which number do I love to test with? 0. So let's test with the 0, guys. Is 0 greater than -3? Yes. Is 0 less than 2? Yes. Because notice I answered yes to both questions, that means that this region is true. Now, let's try a different region. Let's try 5 over here. Is 5 greater than -3? Yes. Is 5 less than 2? That's a no. So then this region must be false. And the region to the left is also going to be false. As we move through this class, guys, you will realize the majority of the time, the truth values, they alternate. So since the middle region is true, that means the region to the left and the region to the right will be false. So now, guys, let's go ahead and graph this. The true region is the region in the middle and between -3 and 2. So to graph this, we are going to use a bracket at the -3. Why a bracket at the -3? Because of this. Then we're going to use a parentheses at the 2, +2. Why parentheses? Because of the inequality symbol. Then we got to show these values right there, guys. Okay, all these are the values that will make the problem true. And of course, we have to express this in interval notation from left to right. So from left to right, you would have a bracket with the -3, +2, and then close it off with a parentheses, which means it's not included. All right, guys. So now I am going to look at an example with you, something you probably will see on the test, so pay careful attention to this next one right here. And guys, remember we are meeting in the classroom in A125 next Monday. All right, guys, so here it is. It is -2 is less than or equal to -5x plus 3 less than 13. This is a compound inequality. So the first thing you need to do is to go ahead and solve for x. It just means that you need to isolate the variable in the middle. So rather than having 2 regions to this problem, you now have 3. You have the left, the middle, and the right. Whatever you do to one region, you must do it to the other 2. So we start off in the middle because the goal is to isolate the x in the middle. So we're going to get rid of the 3 first by subtracting 3 to the middle, to the right, and to the left. So this simplifies to -5 is less than or equal to -5x less than 10. Now, I am going to divide both sides by -5, not both sides, every region by -5, okay? So now, earlier someone had asked the question, I forgot who asked the question, do I need to reverse the inequality symbol every time I divide? And my answer to that was no. It only happens in certain cases, such as this one right here, where we are actually dividing by a negative. So you only reverse the inequality if you divide or multiply by a negative. And so yes, on this one, I'm gonna have to reverse the inequality symbols because I am dividing by a negative. So -5 divided by -5 is 1. 10 divided by -5 is -2. Now, guys, the problem is done. The only thing is, if you look carefully, you have the +1 on the left, the -2 on the right, which means it's not in the correct numerical order. So you may want to rewrite this so that the +1, okay, is on the right because you want this in increasing order, and then the -2 is on the left. Now this makes more sense. And if you can go directly from the inequality to your interval notation, great. If you can't, that's okay. You can go ahead and graph it first. So if we're writing this in interval notation from left to right, we do a parentheses with the -2, comma, the set of values continue to +1, and we're going to close it off with a bracket. Why? Because the +1 is included. So guys, this would be your answer in interval notation. Now, take a moment, guys, look at this. Ask this question to yourself. If I were to see this problem on a test, would I be able to solve this and get the correct solution? If you can't, you should be asking a question. Anybody?
In regards with the bracket, so you said you close it off because you're including the +1. Is that because
Yes.
it's parts? So
because of this.
Oh, so when it's greater than or equal to and you're including it, you do a bracket?
Mm-hmm.
Every scenario or only certain? Yeah?
Yep.
Okay.
Yep. And if you've got less than or greater than, use parentheses.
Oh, okay, great.
Mm-hmm. All right. Now, guys, we're good, or do you want me to do another example?
I'd like another example.
All right, so here comes another one. This is going to be example number 2 then. -11 is less than 2x minus 1, less than or equal to -5. Now on this one right here, I want to add 1 to the middle, 1 to the right, 1 to the left. So this simplifies to -10 is less than 2x, less than or equal to -4. And I'm going to divide everything by 2. So this simplifies to -5 less than x less than or equal to -2. Now, I want to point out the fact that I did not reverse the inequality symbols. Now, why didn't I? Because I didn't divide by a negative. I divided by a positive. So therefore, I don't have to reverse the inequality symbol. So guys, the solution set for this one in interval notation would be parentheses with the -5, comma, -2, and close it off with a bracket. Any questions?
Yes, I have one more. So when it's 3 parts, the goal is to isolate x.
Yes,
correct?
isolate the x in the middle.
All right, thank you.
No problem. All right, guys. So here comes the next compound inequality. And this next one right here, guys, we're not going to do an example for it. This is going to lead us to the absolute value inequalities. So we're talking about the union now. The union, referencing the word or, and the symbol we use for this, I really like it, is the U for union. So when we talk about the union of two sets, guys, we're looking at all the elements from two sets combined. So in other words, you are taking the elements from set A and set B, and you are combining them together to create a larger set. And as with the intersection, guys, the best way to explain this is through a Venn diagram. So here comes another Venn diagram. Okay, very similar to the previous one. We got set A and set B. Now set A has the elements 1, 2, 3. B has the elements 2, 3, 4, 5. Now if they were to ask you for the union of set A with set B, as in what elements are in both of these sets combined. So another way of looking at this is to say the elements can be in set A only, they can be in set B only, or they can be in both sets. So all the elements from both set A and set B combined together will give you this list of elements: 1, 2, 3, 4, and 5. So everything from both sets combined. So guys, again, the elements can be in A, they could be in B, or they can be in both sets. So as long as it satisfies one of those three, it's part of the solution, the union of A with set B. Now, how does this look like with an inequality? So let's go ahead and look at an inequality, guys. I am going to erase part of this here so we can address the inequalities. Now, on this one right here, if we have x is less than or equal to -3, or x is greater than 2, we go to the number line, guys. Remember, we only need one of these sets to be true for it to be satisfied. So here's 0, my -3, and then my +2. Once again, this divides the number line into 3 regions. So we're going to test each region. This is region 1, region 2, region 3 right there. And my favorite number to test with is 0. So I'm going to test with the 0. Is 0 less than -3? No. Is 0 greater than 2? No. So that's a no, that's a no. So this one right here, this region in the middle, false. So then, let's move on to region 1. Region 1, I'm going to choose -5. Is -5 less than -3? Absolutely. So because it makes this one true, that makes this region true. This region is true. And guys, you don't even have to test it with the other one because you only need one of these inequalities to be satisfied. So let's move on to the third region. Let's choose 5. Is 5 less than -3? Nope. Is 5 greater than 2? Absolutely. So this region is also true. So this means that the solution set would be in region 1 and region 3. So now we're going to graph it. Now, according to the inequality symbol, you want to include the -3. So this is what the left side would look like. According to the inequality symbol here, you want to exclude the 2. So this is the other part of the inequality, guys. Now, we have our graph. Once we have our graph, we need to express this in a notation. But I want you to be careful with this one because you notice when we're looking at the graph, it is a disconnected interval, guys. So there's 2 different intervals. We have an interval to the left and an interval to the right. So we got to show that these 2 set of intervals belong to one solution. So when we express this, we're going to do -infinity up to -3, close the bracket off. And then the other interval goes from +2 to +infinity. And to show that these 2 intervals, they are part of one solution, we're going to unify them together. We're going to use that union symbol in the middle to show that this represents one solution. And yes, guys, we are going to be talking about these some more, but this is the union. So 2 types of compound inequalities: intersection and union. Now, I am going to go directly to the absolute value inequalities so we can look at some examples of the union because it's easier that way. So, the absolute values, guys, just like with the compound inequalities, there's 2 of them. Absolute value inequalities. Okay, the first one I'm going to start with is the absolute value being greater than some number. When the absolute value is greater than, this means you have a union. Remember, the union uses the word or, guys. So when we talk about the absolute value being greater than some number, this means either you're going to have values that are greater than C or values which are less than Notice I'm reversing the inequality symbol, negative C. So I did two things, guys. First, I reversed the inequality symbol. Second, the positive C over here becomes a negative C. So I did two things to the second inequality. So when you write out your inequalities, be careful. Remember, when we first talked about the absolute values, we said you typically come out with two solutions. So on this one right here, guys, let me give you a more concrete. All right, remember the first time we talked about absolute value has to do with distance of a number from 0 on the number line. So if I were to go to the number line, guys, and I ask you, what numbers have a distance of more than 4 units from 0 on the number line? That would be everything greater than positive 4. Let me use a different color here. Everything greater than positive 4 would be all the numbers that have a distance of more than 4 units from 0 on the number line. But because we're dealing with the absolute value, when you take the absolute value of a number, guys, it always turns out to be a positive because we're talking about distance. Distance is always positive. You also have a set of values over here on the left, such that when you take their absolute value, they will be positive. So the set of numbers that are less than negative 4 will also make this true. Now, if you do not believe this, or you can't see why, test it out. Test out a value, like negative 10. If I were to take negative 10, guys, and plug it in here, okay, and take its absolute value of negative 10 is 10. Is 10 greater than 4? Absolutely. So essentially what just happened, this problem right here produced two set of solutions. We've got the set of values greater than 4 or the set of values less than negative 4. And guys, there's your two inequalities right there. And of course, you have to express this in a number notation. So an n of notation would go from negative infinity up to negative 4, close the parentheses, and then union from positive 4 up to positive infinity, and then close off the parentheses. And just like that, we're done. Questions, guys? I know. Where's the problem that's going to be on the test? Okay, here it is, everybody. So this is similar to one of the questions you're going to see on the test. It's 3 times the absolute value of x minus 1 plus 2 is greater or equal to 8. And so on this one, they want you to solve it, graph it, and write the solution in interval notation. So the first thing we need to do is to isolate the absolute value, get the absolute value by itself. Subtract 2 from both sides, guys. So you get 3 times the absolute value of x minus 1 is greater or equal to 6. Now this 3 coefficient, this 3 in front of the absolute value, guys, you need to get rid of it. To get rid of it, we're going to divide both sides by 3. Divide both sides by 3. So this cancels out, leaving you with the absolute value of x minus 1 is greater or equal to 2. Now, once you isolate your absolute value, then you can break it up into two inequalities. Now, x minus 1 is greater or equal to 2. That's the first inequality. Be careful when you write the second one. Or x minus 1. Notice I didn't change the x minus 1. It's still the exact same thing. But I am going to reverse the inequality symbol and change that positive 2 to a negative 2. Why? Because there are two numbers that would produce positive 2. Absolute value of 2 is 2. Absolute value of negative 2 is also 2. So now I'm going to solve them, guys. So I add 1 to both sides. So I get x is greater or equal to 3. Over here, I add 1 to both sides. I get x is less than or equal to negative 1. So there's your solutions. Now you have to graph them and write it in interval notation. So the graph, guys, let's look quickly over here. So I want everything less than or equal to negative 1. And then everything greater or equal to positive 3. And then I am going to write this in interval notation. So in interval notation, I'm going to have negative infinity up to negative 1, which is included, and then union from positive 3 up to positive infinity, which is excluded. And there you go. When you're typing these answers into my math lab, guys, be careful with the parentheses and the brackets.
I have a question.
Uh-huh.
So every time we have the absolute value, we have to make one negative and then flip the sign, and then the other
Yes.
one positive and keep it as is, right?
Yeah, the first one, we're basically keeping it as is, except without the absolute value. But the second one, we're doing two things. We're reversing the inequality symbol and then doing the opposite of that value. Why? Because when you take the absolute value of a positive or a negative, you get the exact same number. So in other words, 2 and -2 will give you the same value when you take their absolute value.
Okay.
All right. So guys, here's the last part of it. That was the only, that was the first type of absolute value inequality. So here's the second type, and that is the absolute value is less than C. When the absolute value is less than C, guys, okay, this reflects the intersection of two sets. When we talk about the intersection of two sets, we're looking at the word end. So guys, when you are talking about this, when you break it up, it's going to reflect every value less than C, and there's the operative word again, every value greater than -C. So in other words, when you write this interval, when you're looking for values that are going to satisfy both of these inequalities, you must make sure, okay, use the word end, okay? So if I wanted to show you a precise example, like the absolute value of X is, let's say, less than 3. I want numbers that have a distance of less than 3 units from 0 on the number line. So let me go to the number line. If we go to the number line, guys, here's 3. Here's my 0. We want every single value that have a distance of less than 3 units from 0 on the number line. So we want everything less than 3. But the big question is, can we go indefinitely to the left to find every single value that's going to be less than 3, that's going to have a distance of less than 3 units from 0 on the number line? Well, we can't go on indefinitely. Let's say we get to -5 over here. If you take the absolute value of -5, is it going to satisfy this? It will not, because 5 is definitely not less than 3. So at some point you have to stop. The question is, where do you stop at? You stop at -3. You stop at -3. Because at -3, guys, it would make this problem false. At -3, you would have a value that's precisely 3. So anything equal to or less than -3 will not make this problem true. So the only values that will have a distance of less than 3 units from 0 on the number line would represent everything less than 3 and everything greater than -3. So you have to put this restriction on there. If you don't put this restriction on there, you will encounter values that will not make it true, guys. So once you have your graph, again, you have to express it in interval notation. So in interval notation, from left to right, you start off with a parentheses at the -3, which excludes it, and then you move to the right towards +3 and exclude the +3. So everything between -3 and +3 will have a distance of less than 3 units from 0 on the number line, guys. And that is the second type of absolute value inequality, guys. And that's pretty much it. Now, I didn't even want to do an example with this one because there's really no point in doing it, because we've already done some intersections, problems involving intersection with the compound inequalities. So I think I'm going to leave it here unless somebody really, really wants me to do a problem. Okay, that sounds like you guys want me to do a problem. So I'm just gonna do this one, okay? This one might not lend itself really well to what we're talking about, but we know it does reflect the compound inequality. So let's look at this one, guys. This one's a little challenging. It is one of the questions in the assignments. I don't remember which question it is, but it's in the assignment somewhere. So guys, on this one, the first thing we need to do is to isolate the absolute value by dividing both sides by -2. Now, did you guys hear that? I am dividing by a negative. So what's going to happen with the inequality symbol? I'm going to have to reverse it. Yeah. So now it's greater than. And if we're talking about one that's greater than, guys, this is actually a union. So when you write it out, it's going to be 5 minus x is greater than 3. That's the first inequality. Notice it's almost the exact same thing as the original problem, except without the the absolute value bars. So the second inequality is going to be 5 minus x. I didn't change what's inside the absolute value, but I am changing the inequality symbol. I am changing that +3 to a -3. And now I'm going to solve both. So I subtract 5 from both sides, guys. And look at what I'm ending up with. -x is greater than -2. I'm not allowed to have a negative variable. So I have to get rid of that negative variable, either by dividing both sides by -1 or multiplying by -1. So this becomes x is less than +2. You guys see what just happened there? I had to get rid of that negative by multiplying or dividing by a negative. You're going to reverse the inequality. So guys, this says I want every value less than 2. Now, I am going to do the other inequality. So here I get -x is less than -8. Divide or multiply both sides by -1. So you get x is greater than +8. Any questions, guys? I know.
Yes,
So,
I have a question.
go ahead.
How did you quickly identify that it would be a union? Is it the absolute values that correlate with it being a union, or?
Yeah, the greater than. If the absolute value is greater than, that represents a union.
I'm still a little lost. Is there a different way you could explain it?
Say it again.
I'm still a little lost. Is there
Okay.
a way you could explain it?
Okay, absolutely. Now, think about it to that basic example. This is saying I want every number whose absolute value will be greater than 3. So if you go to the number line, every number greater than 3 would be everything to the right over here. You see that?
Yes.
And then think about the negatives. If I take their absolute value, that would also give me a number that is greater than 3. So anything to the left of the -3 right here will also make this true. You see how the graph is disconnected here?
Mm-hmm.
That represents a union as well.
Oh, okay. So I'll be able to see it visually when I do the line graph.
Mhm.
Okay. Thank you.
Most of the time. I'm not going to say 100% because I don't like using the ultimate terms in mathematics.
Oh, no worries. I understand what you're saying though.
Okay. All right. So guys, we're almost there. Let me finish it up. So I've got every value less than 2. I'm going on the number line now. Every value less than 2. Or every value greater than 8. So this is what my graph looks like. And then I have to express it in a number notation. So -infinity up to 2, not included, union, +8 up to +infinity, not included. And guys, there we go. Just like that, we're done. Now, I wanted to show this one to you because I want you to understand, guys, when you're dealing with these problems, you need to have a pretty good idea of what you're dealing with, what kind of problem. Logically, you need to know what you're dealing with because this problem started out with less than. So if we were going based on the fact that less than represents an intersection, we would have gotten this problem wrong. But because once we started manipulating the problem, we realized, wait a minute, this is greater than, it's actually a union, okay? That completely changes the problem, okay? So math requires a lot of versatility and flexibility for you to deal with it, guys. So you have to be able to think critically about these problems when you're doing these problems. Don't just do the problem without thinking about what you're doing, what sense it makes within the context of the problem. You have to be thinking about those things, okay? Like I just answered Jennifer's question, why is it a union, okay? Why do we have to have two different intervals right here? You know, things like that. So make sure you're thinking critically as you're navigating through these problems, guys. Now, since we're talking about critical thinking, let me go ahead and drop a couple of items, maybe 3 of them, on you guys, and you guys tell me what you think. If you were to get a problem like this, what would the solution set be? The absolute value of x is less than 0. What numbers have a distance of less than 0 units from 0 on the number line? What do you guys think?
Is it all the negative numbers?
Well, what happens when we take the absolute value of a negative number?
There's no
Turns to
solution
positive.
Let's do a
set.
positive.
Yeah, it turns positive. So in other words, this is saying, can a positive be less than 0? Absolutely not, okay? That's impossible because absolute value is always positive. This one will not have a solution.
Oh, okay.
No solution. What if it was the absolute value of x is greater than 0, guys?
Wouldn't that be all real numbers?
Yes, but what about 0? Is 0 greater than 0?
So
No.
would it be a union -1 to infinity, or negative infinity, comma, -1, union 1?
You're almost there. I
I
hear
don't think
you.
there's any negative infinity because you can't go negative after 0. So would it
Okay.
be
It's
0?
all reals, guys. You just have to put that exception in there. The exception is this, 0. The answer can't be 0. So Jennifer's point is, how do I write this in interval notation? You can include everything except 0. Did you hear that? You can include everything except 0. So this is what it would look like if you can include everything except 0. And then, if you have this one right here, okay? This one right here would be all reals. Yeah, because that's greater or equal to. That would be all reals. Mm-hmm.
So that would be the answer on a test if it would be all reals if it had a like I don't know it was greater or equal to.
Yeah.
And then you
Greater
would.
or equal to 0.
Okay.
Yeah. But you're not gonna get one like that on the test. All right, guys. So I think this is it. I'm gonna stop here.